Alright, so today we will be continuing with Bernoulli's equation. Last class we learned about conservation of mass and conservation of energy. So Bernoulli equation is the equation related to the conservation of energy. So to remind you back, the equation for Bernoulli should be like this. Okay, P1 is equal to rho g plus Z1 plus V1 square over 2G equals to P2 over rho G plus Z2 plus V2 square over 2G. Okay, so the idea for Bernoulli equation is whatever that you have at point 1 in terms of energy and at point 2 should equal each other, meaning total energy at point 1 should equal to the total energy at point 2. So, total energy at point 1 should equal to total energy at point 2, meaning the whole equation over here on the left side, the addition of every single item over here should equal to the addition of all the items over here. So, this is the equation for Bernoulli equation. And from here, I've given you the 4 limitations for it. And right now, I would like to give you for right now, I would like to give you the 4 different conditions of Bernoulli equation. Okay, so for number 1, this is in terms of reservoir or tank, which means that we have large amount of liquid. Okay, for example, if I draw a tank like this. Okay, for number 1, the condition for number 1 is the pressure over here, if you are talking about P absolute, it should equal to P, for example, PO is absolute, should be equal to P gauge plus P ATM. Since this is a surface that meets atmospheric pressure, it means that the gauge pressure over here should equal to 0. So over here, this is equal to 0. So PATM stays as PATM. So if you're talking about P absolute, it should equal to PATM. However, because we are dealing with this in terms of gauge pressure, so for our study, P gauge is equal to 0. So what we will have is, for the whole study of Bernoulli equation, we should assume that P at surface should equal to 0. Okay, that will be the first condition for our study in Bernoulli equation for our subject. Number 2, it is also involved reservoir and tank. Okay, so number 2, if you have a velocity at the surface, okay, so velocity at the surface of tank or reservoir should equal to 0 also. Meaning, we assume because we have a very large amount of water, so the movement of liquid going down and up from the system should be relatively small to the movement inside the pipe. So we assume the velocity at the surface of tank or reservoir should equal to 0 also. So first one is we are using P gauge instead of P absolute. So we use the P surface to be equal to 0. Number 2, velocity at the surface of tank or reservoir, because the movement or the velocity is really low relative to the velocity inside the pipe. So we assume the velocity at surface equals to 0. Number 3, if you have a pipe with same surface area, okay, so you will have condition of, for example, like this. Okay. Okay, so if the surface area for point 1 and point 2 is the same, so we can assume velocity at point 1 is also the same as velocity at point 2. This one comes from the equation Q1 equals to Q2. So A1 V1 equals to A2 V2. So if both A1 and A2 is the same or are the same, so V1 and V2 should be equal to each other. So this is where we have this assumption or condition over here. Okay. And number 4, I put it here. If the location of study is at the same elevation, okay, so Z1 should equal to Z2. The elevation head will be the same. So it means that we can cancel out from the Bernoulli equation. Okay, so if the location of study is at the same elevation, Z1 equals to Z2, the elevation head will be the same. So we can cancel out the elevation head for both sides of the equation. That will be the 4 different conditions of Bernoulli equation. So these conditions are really important because later on, if you do not cancel out, for example, the P surface equal to 0 or V surface equal to 0, sometimes in the Bernoulli equation, you will have multiple unknowns that you cannot solve. Because if you only have one equation like this, we can only have one unknown. If you have more than one unknowns, it means that you cannot solve this equation because Bernoulli equation is just an equation between 2 different points. We cannot do 3 points at the same time. It's only between 2 different points. So it is really important to remember all 4 of these conditions. Right, so continuing from that particular conditions, I will do an example that will represent all the conditions that we have just now. Okay, so the example over here involve a picture of a tank, and if you see this opening over here, it means it allows air to come in and out from the system. So this is air rate. So we have ATM pressure inside. And we have a tank, a large amount of liquid. A is the surface of the tank. B is the location of liquid inside the tank. And the liquid that we have over here is water. Okay. And C over here is above B. D, the same location as B or elevation as B, but it is inside the pipe going down. The pipe diameter is 40 millimeter. E is at the floor of the system. F is the nozzle. Okay. So what we are trying to show to you here is we are using a siphon in order to bring out the water from the tank to the outside. Okay. Now we want to find out what is the pressure at point B up until point E. Okay. and the pressure at point F is equal to 0 over here. It's given. Okay. Okay, so in order for us to do this calculation, first we need to find out a few information. Number one, what is the pressure at point A? It is not asked here because based on our conditions just now, we assume the whole study is based on gauge pressure. So PA should equal to 0. Okay, and PF also equals to 0. Why? Because as long as we meet the atmosphere, the pressure should be equal to 0. This is the same thing also. If we meet the atmosphere, the pressure should equal to 0. Okay, so to understand this, simple. As long as the liquid is meeting the atmosphere, doesn't matter at the surface of the tank or at an opening of any opening inside the pipe, the pressure should be equal to 0. Okay, and then we know the diameter over here is 40 millimeter. So let me change it into meter. So this should be 0.04. Okay, so this should be 0.025 meter. This is DI. This is DO. Okay, and then now we are ready and we can start and do the calculation. Okay, so calculate the volume flow rate through the siphon and the pressure at point B until E. Okay, to do this calculation, first, I will find out which of those 1, 2, 3, 4, 5, 6 points that can be compared to each other in terms of Bernoulli equation to get a certain amount or value of velocity or certain value that we need for the other calculation. So first, because PA and PF, both of them are 0. So whenever we want to do a study of Bernoulli equation, we want to find or to try and get the least amount of parameters inside the Bernoulli equation. The meaning of the least amount of parameters means that a lot of the things inside the Bernoulli equation can be cancelled out. For example, if we do between point A to point F, okay, we compare between these 2 points, so you'll get PA over rho G plus ZA plus VA square over 2G equals to PF over rho G plus ZF plus VF square over 2G. Okay, so PA should equal to 0. PF should equal to 0 also. Okay, and then we have VA square, all right, based on the definition or the conditions that we have. Since VA is at the surface of a liquid, this should be equal to 0. Okay, and one more thing is, because F is at the floor of the system, the elevation should also equals to 0. So all these items are 0. Okay, so what we'll have at the end will be ZA is equal to VF square over 2G. So this becomes a very simple equation. And from here, we can actually find what is VF. So to find out what is VF, I bring this question up here. So VF should equal to 2G multiplied by ZA and then square root of it. So 2G is just 2 times 9.81. ZA is equal to, so the Z should be 1.2 plus 1.8. Okay, so then we will get the answer. VF should equal to 58.86. 58.86, and then the square root of it, 7.672 meter per second. That will be the answer for VF. Okay, so once we get VF, we should be able to find out the first question, which is what is the volume flow rate through the siphon? Okay, since the volume flow rate should be the same throughout, so we can use F even though the diameter is different compared to the siphon. So we can just do Q is equal to AF multiplied by VF. So this is a siphon, so it should be based on the equation of pi r square or pi d square over 4. So the area pi, the diameter is 0.025 square over 4 multiplied by 7.672. Okay, so Q is equal to, baik, okay, 3.765 times 10 to the power of negative 3 meter cube per second. So this should be the answer for question number 1, which is what is the volume flow rate. So now when we get the Q or volume flow rate for this particular study, so we can actually find out the V for the siphon. Okay, so V siphon should equal to Q divided by area of siphon. So 3.766 times 10 to the power of negative 3 divided by pi 0.04 square over 4. So V siphon should equal to okay, so Vs or V siphon should equal to 2.997 meter per second. Okay. So when you already get the V for the siphon, which is at point B, C, D, and E, the velocity should be 2.997 over here. Now we can actually try and calculate for pressure from point B up until point E. Okay, how do you do that? Okay, we need to do a comparison between 2 points for the Bernoulli equation. So which point should be the best to do comparison? We find the simplest point in the study and we compare it with the point where we need to find out the pressure. Okay, for example, the pressure that we want to find out is at point B. So we need to know what is the comparison that we can do. So point A over here should have the simplest form. Why? PA equals to 0. VA is also equals to 0. We only have ZA to calculate. So that will be the simplest one. So what do? Is we do Bernoulli equation from point B to point A. Okay, so for example, PB equals to rho G plus ZB plus VB square over 2G equals to PA over rho G plus ZA plus VA squared over 2G. Okay, so based on the conditions, we can cancel out both of them, PA and VA. For this point, PB and VB, we cannot cancel because it is inside a pipe, so the pressure should be different. Okay, but there is one thing that we can cancel out. Since the location of A and B is the same, meaning the elevation is the same, So ZB and ZA can be cancelled out, since you can see A and B has the same elevation. Okay, so you will end up with the equation PB over rho G plus VB square over 2G equals to 0. Okay, so we want to find out what is PB. So PB is equal to negative VB square over 2G. Okay, and then we multiply by rho G. Okay, so this should be a simple equation. So negative VB over here is 2.997 divided by 2 times 9.81. Remember, this is a negative sign. Do not put it inside here, because if this is negative 2.997 and then you have 2.997 square over here, it will become a positive number. Okay, so make sure this is a unit of a negative sign. So make sure it is outside of the calculation. And the rho for water is 1000 and G is 9.81. So PB should equal to negative 4490.67 Pascal. Okay, so this will be the answer for PB. What happened here is B is inside a pipe. So in order for the liquid to get into this pipe, B should be in negative answer. Why? Because PA, this is gauge pressure, PA is equal to 0. Okay? If PB is equal to something that is positive, A will not be able to come into B. Whatever liquid that is inside B will come out to A. Okay? So B should be in negative form so that the pressure is lower than P ATM. So the pressure from the atmospheric pressure will push the A into B. So that's why PB should be negative. Okay. So that will be for PB. So we have a long way to go. Next, we'll do for PC. To find out PC, we can do an estimation that PC should be having a bigger number in a negative form, because it needs to be lower than the pressure at point B. And once again, we compare PC, compare it with A. So PC plus ZC plus VC square over 2G is equal to PA over rho G plus ZA plus VA square over 2G. Okay, so from here, we can do a simple cancellation again. Okay, C is at the top, PC and VC. So we should do the calculation. PC equals over rho G plus ZC plus VC square over 2G equals to ZA. To find out PC is equal to ZA minus ZC minus VC square over 2G. Everything should be multiplied with rho G. Okay, so this is equal to ZA minus ZC. ZA is just now 1.8 plus 1.2. Minus ZC, 1.2 plus 1.8 plus 1.2. Okay. Alright. And then minus VC. V just now is 2.997 square over 2 times 9.81 multiply by 1000 times 9.81. Okay, so PC should equal to okay, so the answer for PC should be negative 16,263 Pascal. Okay, so as we assumed earlier, PC is lower than PB, so that the liquid should move from point B to point C. If PC has a higher number, meaning if the PC is having a number that is much smaller than this number, for example, this is negative 4490. If PC is negative 2000, PB, liquid from PB should not be able to come out to PC. So because PC has a bigger number over here, which is negative 16263, but in a negative condition, so PC is lower in pressure, it means liquid can come out to PC. Okay. The next one for this should be PD. And PD should be a very simple condition. Why? Because B and D is at the same location. So if you are talking about point B and D, since both of them are at the same location or same elevation, inside a pipe, okay, so what will happen here is we will use the information that we studied in chapter 2, which is in terms of pressure. Pressure, if you have it at the same elevation, assuming this is a pipe, a continuous pipe, and both of them have the same elevation, for example, 0.1 and 0.2, the elevation should be the same and the pressure should be the same. Okay, this is based on chapter 2. Alright, so for this particular study, since Z1 equals to Z2, P1 should be equal to P2. We can actually use this information and we can get PB should equal to PB So for this particular study, for point B and D, so we can get PB should equal to PD. Okay, so if you want to check whether it is the same or not, you can do the whole calculation. But since we are using the idea from fluid static, which is the idea of pressure at the same elevation should be the same, as long as it is in the same condition, which is for this example, both of them are inside a pipe. Okay, so PB should equal to PD. So that will solve the problem for B and D. Okay, and the last one, we need to find out what is PE. Okay, so to find out what is PE, so I'm using different color over here, and we do it down here. So let me draw line. Okay, so lastly, we do between point E and point A. So we will get PE over rho G plus ZE plus VE square over 2G equals to PA over rho G plus ZA plus VA square over 2G. So these two can be cancelled out, and then E should be at the bottom, so meaning ZE should equal to 0. And we will end up with this equation, PE over rho G plus VE square over 2G equals to ZA. So if you bring it up here, the equation for PE should equal to ZA minus VE square over 2G, and then the whole equation will be multiplied by rho times G. So equals to ZA is 1.2 plus 1.8 minus VE should be 2.997 over 2 times 9.81. Okay, and then multiply by rho 1000 times 9.81. Okay, so PE should equal to okay, so PE should equal to 24,938 Pascal. Okay, or for my calculation, it should be a 9. Okay, 24939 Pascal. So that will be the answer for PE.